perspective transformation. This has everything to do with the way we project onto the screen, our imagined lens of the camera, how wide this lens is, which area in front of us we're actually taking and which area we're going to actually project onto the screen, and how we're going to set up the boundaries of this area to clip away everything that's outside the screen and focus on what's inside. And the basic idea is we're taking our 3D scene and we're projecting it onto a two-dimensional plane. And in the image we can see that we're working with the eye in the center of the global coordinate frame. The eye is now the center of the universe. We don't care about our local coordinate frame or our camera's coordinate frame. The only thing we're looking at now is we're imagining the eye to be in the center of the universe. We're projecting everything along the z-axis. We're looking along the negative z-axis. And we're going to set up the two-dimensional coordinates in our viewport. That is the two-dimensional coordinates in the screen that we're watching. For each three-dimensional object, or for each three-dimensional vertex out there in the world, we're going to set up a set of two-dimensional coordinates for where it should end up on screen. And like you see here, we basically take a line from the point P in three-dimensional space towards the eye, and the spot where that line intersects with the screen or the near plane is the location of the two-dimensional coordinates on screen. So basically the point that we see the point P through the near plane. So if we look at this scene here, and for starters just focus on the height, just the y and the z parts, or in this case actually the x and the z parts, we can basically imagine similar right triangles, and we can take the ratio between the distance to the near plane and the height or the distance in either x, y to the point where we want to project it onto the near plane. That is the x star and the y star coordinates. That would be the smaller right triangle. The larger right triangle would be have minus pz as the baseline, where the distance as n is in the smaller triangle, and the x and y coordinates of p would be the other side of the triangle. So we can take these ratios and say if x star divided by the x coordinate of p should be the same ratio as n, which is the shorter distance out, divided by minus pz, which is the longer distance out in this picture. So these ratios, this ratio should always be the same, and thus we can calculate x star as n times px divided by minus pz, and the same for the y coordinates. So the simplest perspective transformation is simply this. We take the x coordinate of the point that we're projecting, we divide it by minus pz, and the minus is there because we're looking along the negative z-axis, so minus pz will be a positive value if the point P is somewhere where we're interested in it anyway. So we divide it by that length, the distance from the eye to the point, and we multiply it back up with the distance to the near plane where we're projecting it onto. So we're projecting the x coordinate back from where it is onto the near plane, and we do the same for the y coordinate and end up with these points. So on any arbitrary near plane, we can basically project any points onto this. We haven't taken into consideration how wide the lens is or how high. We haven't taken anything into consideration except we've taken the whole world and projected it onto the near plane, which is this basically this xy plane, which is translated the amount n along the negative z-axis of the coordinate system. So once we have this basic projection, we can look at where in the OpenGL pipeline we're actually going to do this. So we want this to happen in the projection matrix. We have I-coordinates after we've done all the model view matrix calculations, or that is the model view matrix multiplication, a single multiplication which takes all our coordinates and represents them in the camera coordinate frame. Then we have I-coordinates. In I-coordinates between VM and P, we do some calculations. We do lighting calculations in fog and more stuff there. But what we're interested in here is that the I-coordinates themselves, the positions, are unchanged when we go into the projection matrix. And we want another matrix multiplication, just like the model view multiplication, another matrix multiplication that can project for us, that can make X star and Y star for us, and do certain other things as well. So to begin with, we're going to look at how can we perform this calculation, X star equals n times px divided by minus pz, and the same for y. How can we do this as a matrix multiplication? So that's our first problem. Before we look into that, since we're going to do a three-dimensional matrix multiplication, we'll look at the third value and what we do with it, because we're taking 3 dimensions and we're changing them into 2 dimensions. But in order to do to set up our depth buffer later on in the rasterization phase and be able to actually determine which objects are closer or further away in the screen, so which pixels should be drawn and not drawn based on something else being in their way, we're actually going to need to keep track of that third dimension in some way. Although we're not going to actually keep the z-coordinates, we're going to take some representation of the distance and store that, and we're going to try to calculate this in this same single matrix multiplication as well. So everything simply to optimize the OpenGL pipeline or the graphics pipeline. We're going to try to do this all in one calculation. So looking at the distance, calculating the real distance is possible, but that's fairly expensive. Just keeping the z-coordinate would actually be plausible as well. So even though it's not the true distance, any point that will end up in the same pixel will have the z-coordinate or the z-distance longer if it's further away and shorter if it's not. So that would be usable. But we have one more criteria, and that is that in order to do everything in a single matrix multiplication, it's going to be simpler for us to do it if we can have the same denominator on all of the coordinates. So adding this third dimension here, z star, we want somehow to set it up so that it has the denominator minus pz. And seeing as using just pz or minus pz, the distance to z, as a numerator, that would always give us 1, so that's not good enough. But it's possible to set up some linear numerator function of pz divided by minus pz and actually get a value that we can use. And not only a value that we can use, but a value that can actually be very useful to us, the way this function ends up looking. So we call this pseudo depth. And the pseudo depth value, we want it to be set up so that values that we're interested in, that is values that land between the near plane and the far plane, which are the planes that we clip away on z, values between -1 and 1 are going to be what we're interested in. So anything that lands on the near plane should get a pseudo depth value of -1, and something that lands on the far plane should get a pseudo depth value of 1. And we can see on the graph that thing that will happen is that things that are closer to the far plane will actually get less detail in possible values. That is, the values will be much closer together, whereas values will be more distant. Values that have the same x value here on the graph, or have the same distance between x values, will have a greater distance between y values closer to the near plane. So the detail in data will be more closer to the near plane but less closer to the far plane. And because we're actually using discrete values, so to speak, since we're using either floating point numbers or integers or some numeric binary value to represent this data, it can actually matter that we have more detail in this data closer to the near plane, so that we don't get what's called z-buffer fighting, which is basically an effect that two objects which are very similar to being as far away from the eye, they're very close to being at the same length away, that they end up getting the same pseudo-depth value. And if you get the same pseudo-depth value, you don't know which pixel will be shown and which pixel won't be. So closer to the near plane, it's best to not get much of this z-buffer fighting, whereas closer to the far plane, it's less of a hassle, since things are less focused on anyway in the image that we're setting up. So these values are not something that is necessary to learn or understand exactly how are derived. But we set up these a and b values here, and we're going to set up this linear function, a times pz plus b divided by minus pz, and we can calculate these factors a and b and set them up in our projection matrix in the end to get this exact effect. That is the effect that everything on the near plane will get the pseudo-depth value of -1, anything on the far plane will get the pseudo-depth value of 1, and everything between will be non-linearly distributed between -1 and 1, giving us a bigger or wider range of values closer to the near plane, but a tighter range of values closer to the far plane. So now the question is, can we actually make these transformations with this division with minus pz using homogeneous coordinates and matrix multiplications? And in order to do this, we kind of have to set up a more general description of homogeneous coordinates and say the point px, py, pz, and 1 is the same point as all of these same values multiplied with a factor. So if we can basically scale up this point, and if we scale the last homogeneous coordinate, the last part of it, the 1 as well, then we can simply say, okay, the x, y, and z parts of this are not the right parts of this point. Instead, we have to take the last value and we have to divide the whole thing with that. And by shortening this in a way so that the last value is 1, then we've got the true coordinates of the point. So any homogeneous coordinates a, b, c, d can now be said to represent the 3D coordinates a divided by d, b divided by d, and c divided by d, being the true x, y, and z coordinates, and then 1 in the end. So we divide the whole set with the fourth coordinate and get the true value. So transforming with our regular transformation matrices will be completely unchanged. It doesn't matter where the 1 was still a 1 in the result. Now the w or whatever factor is in the fourth part will still be the same. For vectors, they'll still be 0. But the interesting thing is, now we can actually work with different bottom lines than only 0, 0, 0, 1. Like in this case, if we set up the bottom line 0, 0, minus 1, 0, we can actually see that we're going to end up with minus pz in the fourth coordinate of the homogeneous coordinates, which gives us in the end a division by minus pz, which is actually what we were looking for. We wanted the denominator on all of them to be minus pz, and the reason we wanted the same denominator on all the coordinates was exactly this. We wanted to be able to use this type of homogeneous coordinates, get this division here, and thus use a single matrix multiplication to calculate the projection itself and the pseudo depth as well. Alright, so here's a little recap of the projection calculations so far. To begin with, finding the 2D coordinates on the near plane, which is the screen we're projecting onto. Next, finding the pseudo depth and sticking to this common denominator throughout. And the reason for the common denominator being that we're going to set up a projection matrix like this. And if we can set this minus 1 up in the bottom line of the matrix in the third column rather than 1 in the fourth column as we're used to, we end up with minus pz in the fourth coordinates in the homogeneous coordinates, which represents a division by minus pz throughout all the other coordinate parts. So here we have a simplified version of the projection matrix, because we're going to look at a few more things that we're going to do. So the pseudo depth is set up in a way that is the a and b factors are set up in a way that we end up with coordinates from minus 1 to 1, or pseudo depth values from minus 1 to 1 for everything that's relevant. So something that's between the near plane and the far plane will be between minus 1 and 1. Everything smaller than minus 1 will be clipped away. Everything larger than 1 will be clipped away. And what we now want to do is to do the same thing for the x and y coordinates as well. So the clipping volume is basically this. We can imagine it as a three-dimensional volume, three-dimensional cube that will include everything that we're interested in afterwards. So it's sort of two-dimensional coordinates, except we add this pseudo depth as the third dimension, and end up sort of with a three-dimensional cube. And we want this cube simply to extend from minus 1 to 1 in all directions. In the pseudo depth it already does. And the algorithm that we're going to use is basically comparing with these edge values. And if we can optimize that algorithm to simply compare to 1 and minus 1 every single time by setting up our projection matrix so that it projects the entire scene into a cube of this size, we can make the OpenGL pipeline run that much faster. So let's look at the OpenGL function that actually sets up the projection matrix. So we looked at GLU perspective, and GLU perspective takes in as variables an angle, an aspect ratio, and the near plane and the far plane. And when we use GLU perspective, left will simply be minus right and bottom will be minus top. But what GLU perspective does is it calculates right and left, bottom and top, and uses the near and far coordinate that it has, and sets up the screen, or what the space that we're going to be projecting onto on the near plane in this way. So when it encapsulates the function glFrustum and sends in these left, right, bottom, top, and NF coordinates. And in this function glFrustum, if we call that straight away, it isn't necessary to have left equaling minus right and bottom equals minus top. So we can kind of have skewed areas, or something that mimics like a side view mirror or rear view mirror, something like that. Stuff that kind of looks through the camera only through the side, or through an angle direction. Either way, in order to set up this clipping volume with the variables that glFrustum has, which is left, right, bottom, and top, near and far, what we want to do is we want to translate by half the width, or minus right plus left divided by 2, in order to center it on the x-axis. We want to center it on the y-axis. Then we want to scale by the width, or basically scale by 2 divided by the width. So the width that was originally will now be 2 wide, meaning it ranges from -1 to 1, and the same on the y-axis. So we're going to make translations in scales in order to take the window that we're interested in on the near plane and set it up so that it extends from -1 to 1 rather than from left to right or from bottom to top. And in the end, in order to set up the projection matrix entirely using these transformations as well, this is what it's going to look like. So now we have the full-fledged projection matrix, and this projection matrix basically takes the 3-dimensional values, finds the 2D values on the near plane, and finds the pseudo depth as well. And then it scales the x and y coordinates on the near plane so that they extend, the window that we're looking at is basically normalized to and centered, so that the values that we're interested in range from -1 to 1. We will get values beyond -1 and 1, but those values will be clipped away. So we're basically setting up the clipping volume so we can always clip at -1 and 1 in all 3 dimensions. So this projection matrix is simply exactly the matrix that OpenGL builds when we call glFrustum. And the reason, as we spoke of earlier, for this normalization for everything to range from -1 to 1, to basically scale and translate the window that we're looking at to this specific cube, is optimization of the clipping algorithm, where the clipping algorithm can be programmed basically straight onto hardware in a way that it always compares with -1 and 1 values rather than, or with constant values, rather than having to have variable values in there. And this can really speed up the hardware programmed algorithms on our graphics cards.